All right, so get your holes and asymptotes packet, and we're just going to look at that first page there. So this is just going to be more of a talking and you understanding. It's really pretty simple and basic. A hole, if you read it, where there are breaks or gaps in a graph. And at these points, the rational function isn't defined. So let's look at this picture right here. Do you see that you have a hole at x equals 3? So basically what this is saying is there are x values that work in this entire function except for x equals 3. That's what it means when it says the function isn't defined. So this function is defined at every x value except for x equals 3. Let's look at this one over here. Do you see right here at b we have a hole? And we have a little gap here, okay? And that goes back to this little portion of the explanation. So the graph is not defined at x equals b. The graph is also not defined at x equals c because, again, you have another hole here and here, and we've got a gap here, okay? Now, I want to talk about a for a minute. Do you see that this graph gets closer and closer and closer to A, but doesn't touch it? The same thing with this portion also. So the graph also is not defined at A, but not because it's a hole, but because it's an asymptote. Okay? So this graph is not defined at x equals 3 because we have a hole. This graph is not defined at x equals b because we have a hole, and x equals c because we have a hole. But this graph is also not defined at x equals a because we have an asymptote. And an asymptote is a line that a graph gets closer and closer to, but it doesn't cross over it. And I know that you've done that as well. So that's what this says right down here. So if you look at this graph, we have an asymptote at x equals -1. And we have an asymptote at x equals +1 because the graph gets closer to it but doesn't touch it. Same thing over here. And actually, if you look down here at this portion, it gets closer to it, but it doesn't touch it. Now, we also have another asymptote, if you look, and that's the line y equals 1. And because the graph gets closer and closer to that on both sides here. So this graph is not defined. Okay, a rational function isn't defined at holes or asymptotes. There's one asymptote. Okay, so this graph is not defined at x equals -1, at x equals +1, or y equals +1. So there's 3 points, x equals -1, x equals +1, and y equals +1, where this function is not defined. Alrighty, so now we're back to not having a calculator. So we need to determine holes and asymptotes. If you look up at the top, or you look at the directions, it says find all holes, horizontal asymptotes, and vertical asymptotes for the following functions. But we don't have a graph, and we're not allowed to use a calculator, so we have to come up with like a plan B here. So there's a pretty easy way of doing it. So the first thing that we look at is, let's just go, I put these in order, and I think this is such an easier way to handle any question like this. So our first step is we're going to determine all the horizontal asymptotes. So if you look back on page 1, that bottom picture, the horizontal asymptote was y equals 1. Okay, page 1, bottom of the picture, the bottom picture, y equals 1 is that horizontal asymptote because it's a line that's horizontal. So that's what we're going to try to find. We do something called end behavior. It's really pretty simple. What you do is you look, let's start by looking at the numerator. And I take the highest power of x, in this case in both of these parentheses. So that's an x, and that's an x. If I were to double distribute, do you guys see that that x would multiply with that x, right? And do you see that that would give me x, let's make that look like an x squared. So that's the highest power in the numerator. I know there's a lot of other junk attached to it, but when we do what we call end behavior, we don't really care what the other junk is. The highest power in the top is x squared. Okay, well, we're going to do the same exact thing in the denominator. So we take the highest power in this parentheses, which would be the x, and the highest power here, and just double distribute those. And when you do that, do you see you get x squared again? So this is what we call end behavior. All we do is we take this and we say, all right, well, reduce it. What do you get? And we get y equals, I'll explain that in a second, 1. All right, so let me explain. We're getting 1 because x squared over x squared is 1. That's easy enough. But a horizontal asymptote is a horizontal line, and any horizontal line is always a y equals. So right here, you just write this. This is your, I'm going to put a colon here, horizontal asymptote. Y equals 1 is your horizontal asymptote. All right, now let's look at step 2, I should call it. It says determine all holes by factoring and looking for common factors. These common factors determine the holes in a graph. Alrighty, well, let's look up here and see if we have any common factors. P.S. We don't need to factor this. It's already done for us. That was very nice of them. Do you see that you have a common factor of x plus 5 and x plus 5? So it's these common factors that determine the holes in a graph. So when we want to find holes, I'm going to just write this, holes, all we do is we take whatever the common factor is, which is x plus 5, and we set it equal to 0, and we solve. Really simple, right? So x equals negative 5 is where the graph would have a hole in it. If we could graph it, which we can't. Okay? So if we could graph it, we would know there'd be a horizontal asymptote at y equals 1. And if we could graph it, we know that we would have a hole at x equals negative 5. Okay. Now let's look at step 3, because we're almost done here. Determine the vertical asymptotes. Those are asymptotes that go this way. So if you were looking at the bottom graph on page 1, your vertical asymptotes were x equals negative 1 and x equals positive 1. So that's what we're going to try to find. So it says here, determine the vertical asymptotes. Look at this in bold. By first canceling out common factors, or your holes. So what that means, and I'll read the rest of it in a second, is I'm going to take that x plus 5 and this x plus 5, and I cross them out. Okay? And then from there, let's read the rest of the explanation. So the rest of the explanation says, then set remaining denominator equal to 0. Remaining denominator equal to 0. So the only thing I have left in that denominator is that x minus 1. So then if I want to get my vertical asymptote, I take that x minus 1, I set it equal to 0, and I solve. So this is my vertical asymptote. All right, you just have to remember these first 3 steps up there, and the rest of it isn't too bad. Okay, let's take number 2. I'm going to just rewrite that. So I've got f of x equals, now this one says, actually, you know what? Let me not finish rewriting it, and let me just go back here. And let's look at step 1. It says determine all the horizontal asymptotes by looking for the end behavior. That's the highest power in the numerator, which we found here, and the highest power in the denominator. Well, look, isn't this the highest power? And isn't that the highest power? Okay, so all we have to do is we should be able to see that the highest power in that numerator is x squared, and the highest power in the denominator is x squared, so doesn't that reduce to 1? So your horizontal asymptote, I'm going to write it, squeeze it in up here, your horizontal asymptote for number 2 is, remember a horizontal line is always y equals 1. All right, now let's go to step 2. So step 2 says to determine holes, we have to factor and then look for common factors. Okay, so that's what I was getting at before. I want to factor this. So I see in the numerator that I could take out an x, right? And then I'd have x minus 1 left. And in the denominator, I can do dots. So that's x plus 1 and x minus 1. And here's your common factors, and that's what determines the wholes. Okay, so if you have a common factor, then all you're going to do, remember, is to find a whole, you take that common factor, which is x minus 1, and you set it equal to 0. So the graph, if you could graph it, has a whole at x equals 1. And the last step, make sure you're taking notes. The last step is to find the vertical asymptote. Let's go back here again, determine the vertical asymptotes by first canceling out the common factors, then set any remaining denominator equal to 0. So I'm going to go over here, and I am going to cancel out my common factor. And the only remaining portion of the denominator that I have is that factor of x plus 1. So we just take x plus 1, we set it equal to 0, and we have x equals negative 1. That would be my vertical asymptote. All right, last one for the video. Okay, so to determine the horizontal asymptotes, we're going to take the highest power in the numerator, which is x squared, and the highest power in the denominator, which is x cubed. Now that does not reduce to a number, but what it does reduce to is 1 over x. Here's the thing, I want you to think about this for a second, okay? So when we're finding horizontal asymptotes, we're looking at this graph as it goes further and further and further and further out. So if you think of a number line, as you go further and further out, let's say to the right, don't your numbers get larger, like 1, then 2, then 3, then 4, then 5? So, for example, if I plugged in right here, if I plugged in a number on the number line, really anything, let's say I plug in a 1, I would get 1 over 1, right? Then let's say I go further out on the number line and I plug in a 2, I get 1 over 2, wouldn't I? And then let's say I plug in a 3, I get 1 over 3, don't I? And then let's say I plug in a 4. Do you notice that every time I plug in a number that gets further out on the number line, look at what happens to the value of these fractions. Don't they get smaller and smaller and smaller? When something gets smaller and smaller, that means it's approaching 0. So the little trick is if the power in the denominator is larger, this is x to the first, this doesn't even have a power, so this is larger than this one, then what we do is we say that our horizontal asymptote will be y equals 0. So I'm just going to kind of reiterate that. So again, real quick, if we have a larger power in the denominator than we do in the numerator, our asymptote will always be y equals 0. And the reason being is these values get lower and lower and closer to 0. Okay? All right, now let's look at part number 2. So if we want to do wholes, remember that we have to look for common factors. So I need to factor out number 3. And then this is what I would get if I factor that out. Okay, so wholes, common factors. So I see that I have x minus 4. So then if I want a whole, or find my whole, I should say, I would take that common factor and set it equal to 0. So my whole here is at x equals 4. And then remember, when we want to find vertical asymptotes, we cross out said wholes, and then we look at the remaining portion of the denominator. Ooh, we have 2 terms here, and that's going to not complicate things because it really won't. Oops, oh, okay, I guess I'm writing in red. We take each of those factors and we set them equal to 0. So I actually have a vertical asymptote right there, and my other one is at x equals 7. So we have 2 vertical asymptotes. Okay, and then up here, let me just write this. This is the horizontal asymptote. Okay, make sure you're writing all this down.